Velocity time graphs are one of the more important things that you would learn in elementary physics. This says velocity time graphs in AP Physics, but it's not necessarily for just AP Physics. Any physics student in the early level should know about these things. One reason is because there's so much information packed into a velocity time graph, as you'll be able to see in a few minutes here. Let's take a look at a really simple example of one. We have the velocity here listed in meters per second and the time in seconds. And as you can see, we have a constant velocity of 6 meters per second for 8 seconds. What kinds of things can we learn from this? Well, for one thing, we know that the acceleration is 0 because the velocity is constant, right? And what else can we learn? Well, let's take a look at a question here. What was the displacement between 1 and 8 seconds? Now, displacement, as you know, means the change in position. From 1 second to 8 seconds is 7 seconds, moving at 6 meters per second. Yeah, I think we can figure that out pretty easily. But let's take a look at it in a little bit more complex detail so that if we don't have such a simple graph, we can still come up with answers really easily. The key to understanding what we're going to do is to realize that velocity is the rate at which position changes. And you know that to find the rate of change of any function, what do? You take the derivative of the function. So this is the calculus expression that velocity is the rate at which position changes. We use r, vector r, as the position vector. But if you think about it in a different way, well, let's suppose we multiply both sides by dt. So we would have v dt equals dr. And now what do we do with that? Well, if you've taken some calculus, well, if you haven't, none of this makes any sense. So I'm going to assume you've taken some calculus. You take the antiderivative of both sides. Now on this side, we have the integral of the velocity dt. And on this side, we have the integral of dr, which is simply r2 minus r1. Or in other words, the change in position, the displacement. And so that means we can look at it in the opposite direction. If one thing is the derivative of another, then the antiderivative of the first thing is the other. And so we can say that change in position, as we've just shown, is the integral of velocity with respect to time, the antiderivative of velocity. In other words, this, which is kind of what we just wrote. So that allows us to compute the displacement based on this graph. Now, I'm going to do this in a ridiculous way, but here's the idea. The change in position, I'm going to use x here since we're only moving in one direction, is the integral from 1 to 8, time 1 to time 2, of 6 dt, which is 6t from 1 to 8, which is 6 times 8 minus 6 times 1, which is 42 meters, which you knew 5 minutes ago. 7 times 6 is 42. But the key is, although this method that we used up here works very nicely at a constant velocity, this method works as long as we have the velocity function defined in any way as a function of time. Okay? So we've learned something even if it was a really simple problem. One other thing. We also know that the integral can represent the area under a graph, in this case between 1 second and 8 seconds. And so that area up there, well, that's easy to compute. Of course, it's a rectangle. I want you to pay attention to the units. That area would be a height of 6 meters per second times a length of 7 seconds. And so we would get 42 meters as the area of the graph, not square meters or anything like that. And so because an integral can represent or can compute an area of a graph, we could also say that the displacement, the change in position of an object, is the area under its velocity time graph. So we've actually talked about two things. The slope of the velocity time graph gives us the acceleration. The displacement can be found by finding the area under the velocity time graph. So that's why the velocity time graph is so important. Let's take a look at a better example. Here's a nice little velocity time graph, and I have a question for you to try to think about. Is this velocity time graph indicating an object that is 1, getting closer to the origin, then going beyond, 2, getting closer to the origin, then turning around and moving away, or 3, moving consistently downhill, passing the origin at 4 seconds? Or is it representing something else? Think about that. Choose one of these or choose your own answer. Maybe pause the video to think about it and then come back. Okay, you're back. Let's take a look at what's going on here. At time 0, the velocity of this object is up here at 12 meters per second. After 1 second, it's at 9 meters per second. After 2 seconds, it's at 6 meters per second. After 3 seconds, it's at 3 meters per second. And at 4 seconds, its velocity is 0. Remember, this represents velocity. So it's going fast in a forward direction until it's coming to a stop. Okay? So it would be like this. And then slows down. So right here where it was moving fast, that was at time 0. Right here where it stopped was at time 4. Now what happens? Well, at 5 seconds, it's moving at negative 3 meters per second, meaning it's moving back toward its starting point. Then negative 6 meters per second, negative 9 meters per second, negative 12 meters per second. So that means after 4 seconds, it's starting to speed up this way until after 8 seconds, it's moving at 12 meters per second in the opposite direction. Make sense? Okay. Now I want you to understand something. This is a two-dimensional graph, but one of those dimensions is time. It's representing one-dimensional or straight line motion. So what could be happening here? Well, maybe there's a hill. Okay. And maybe this is an object that's coasting up the hill, but slowing down, slowing down, slowing down, comes to a stop momentarily, and then starts speeding up back down the hill. Worth remembering, when the velocity is positive, but the acceleration is negative, note the negative slope, that means it's slowing down. Down here, the velocity is negative because we're below the axis, and the acceleration is also negative because the slope is negative. There's a calculus idea again. When the velocity and acceleration have the same sign, in this case both negative, the object is speeding up. And so we have a fourth option. It's moving away from the origin while slowing, then stopping at time 4, and then returning toward the origin while speeding up. So if you came up with that idea, give yourself a little pat on the back. Don't hurt your shoulder or anything like that. You've done well. Let's try a third example. Oh, that one's tricky, but this is pretty typical of an AP exam kind of question. Describe the motion illustrated by this velocity time graph, and what is the final position of the object relative to its starting point? Pause the video, take some time, and see if you can work your way through that. Okay, you back? Okay, here's what's happening. For the first 2 seconds, the object's moving at a constant 6 meters per second in the forward direction. So kind of like this. And then after 2 seconds, it starts slowing down until its velocity is 0 at 4 seconds. Then it starts accelerating in the negative direction, and then it moves at a constant velocity in the negative direction. Here's the acceleration in the negative direction. Here's constant negative velocity. And then it starts slowing down because its velocity starts heading towards 0. It doesn't reverse direction there. It starts slowing down. So it's going fast, and then it's going slower and slower. Here its velocity, wherever that point is 0 again. And it starts moving in the positive direction again. It starts speeding up, and then it moves at a constant speed for a while. Speeding up right here, constant speed here. Okay? So here at t equals 4, the velocity is 0, and it changes direction. Here at t equals, well, we'll have to figure out what that is. It changes direction also. It has a velocity of 0. Let's figure out what that point is right there. Let's see, this goes, to get from here to here, this is at the point 7, 6. Make a 6, there we go. And this is at the point 6, negative 3. Okay, so the slope of that little segment right there is 6 minus negative 3 is 9 over 1. It's moving 9 units up when it moves 1 unit over. Slope is change in y over change in x, right? And so that means change in x is change in y divided by 9. But at this point right here, the change in y, this distance, is positive 3. So it's 3 over 9. So change in x, technically change in time, is 1/3. So this is 6 1/3, or 19/3 of a second. Okay? And then, as I mentioned, it starts, after that amount of time, now it starts speeding up in the positive direction and then holds at a constant velocity for a while. So that's the description, and it's all one-dimensional motion once again. What's the final position of the object relative to its starting point? Well, this is where we go back to the idea that the displacement is the area under the graph. We have a positive area here. Let's say this area here is going to be a height of 6 times a width of 2. That's 12 meters. This area, we'll call it area 1. Let's call this area 2. That's a triangle. So it's 1/2 times the base, which is 2, times the height, which is 6. That's 6 meters. Then we have this area right here. That's going to take a little bit of calculating. We'll call that area 3. And we have this area right here. That's going to take some computing. We'll call that area 4. Area 3, as it turns out, is a trapezoid, right? Because this is parallel to this. And so area 3, let's see, how do you find the area of a trapezoid? Is 1/2 times the height times the sum of the bases. So it's going to be 1/2 times, what's the height of this trapezoid? Well, this is a calculus trapezoid. This is a graphic trapezoid. Its height is not 3, its height is -3, because you can have negative areas on a graph, especially in calculus. And then the bases, well, this little base down here goes from 5 to 6, that's 1. Plus the other base goes from 4 to 6 1/3, which is 2 1/3, or 7/3. That's 2 1/3. So this is going to be -3/2 times 10/3. 3's cancel, the 10 and the 2 cancel. That ends up being -5 meters. And so let's figure out area 4. Area 4, well, that's a trapezoid also, right? 2 parallel sides here and up here. This is the height. The height, 1/2 the height times the sum of the bases is 1/2. Height is 6. And then the bases are, well, this bottom base is from 6 1/3 over to 8 is 1 2/3, which is 5/3, plus from 7 to 8 is 1. So this is going to be 1/2 of 6 is 3, times 5/3 plus 3/3 is 8/3. That's positive 8 meters. And so displacement is the total area under, put that in quotation marks, the graph, keeping in mind that areas below the horizontal axis, the time axis, are negative. And so that total area is the total displacement. And so we can say that delta x is going to be 12 plus 6 minus 5 plus 8. That looks like 12 and 6 is 18. 18 minus 5 is 13, plus 8 is 21 meters. So it ends up being displaced in the positive direction from its starting point. So this is 21 meters from here. That's how you use a velocity time graph to find displacement. Any questions? Ask your teacher.